One of the things we're going to start tying into our equations as we do Unit 7a is talking about the domain of your function. We've done this with graphs consistently throughout. We did it a little bit with equations at a different earlier in the year, but we are going to start doing that with all of our equations now to make sure we're tying those graphs and those equations together. For your domain, remember that it's really just the x values that you are allowed. With graphs, we think of this as allowed to plug in to the function. It's also the left and right of your graph. When we're talking about equations, it's very similar. It's the x values you are allowed to get as an answer. This is related to any time you get extraneous solutions or excluded values. One very important thing is the answers you are allowed to get. It's not necessarily the answers you do get. And so we're going to talk about that a lot as we go through. This is something I will address in every single video as we talk about all the different problems, is how you would figure out what you're allowed to get. And then we'll go forward and figure out what answers we actually got. What I'm going to do here is just go through each chapter, kind of remind you what those equations looked like, and then talk about typically what the domain of those functions would be. In Unit 1, going way back, we talked primarily about one type of function. We talked about linear functions. We didn't just do it with your typical, what you may picture as a linear equation, which would be, for example, I don't know, 3x plus 2 equals 8. That is your most basic version of a linear function. We did make it a little bit more complicated than that. What we did is we also made them absolute value equations. We also made them inequalities. We also made them absolute value inequalities. Let's see if this should be an 8 to make my equation make sense. Okay, and when we did these, we talked about really just how that slight variation changes what's happening, whether it's an absolute value or an inequality or both. We did obviously do more complicated ones than this ones, and we will talk about those as we go through the individual notes. As for your domain, what we're thinking about is what x's we're allowed to get as answers. And again, if you're thinking about back to your graphs, what we talk about there is what you're allowed to plug in. So I would want you to think of it like that. If I really just wanted to guess and check this problem instead of actually using the algebra skills that we have, I would have to think about what value I can plug in for x in any of these equations, and then I would just have to do the math until I got a right answer. When I'm doing that, looking at this equation, since it's a linear function, you could plug in literally any number in the world and actually evaluate it. You're not necessarily going to get the right answer for all of those, but you can plug in anything you want. Okay, I can do 3 times a whole number and add it up. I can do 3 times a decimal. I can do 3 times a negative. I can do 3 times anything. What that means for me, if it is a linear function, your domain will always be all real numbers because you can plug in anything you want. It's not necessarily going to be right, but because it's linear, it's negative infinity to infinity. If you're thinking about your graphs for your absolute value or your linear functions, they do go as far to the left as you can and as far to the right as you can. Thinking about Unit 2, this is where we did our radical functions or our radical equations. And for example, this can look a lot of different ways. Again, I'm just going to make some up. X plus 2 is greater or is equal to, don't do an inequality yet, sorry, 4. We also did maybe the cube root of x plus 2 is equal to 4. And any root we wanted. This could also be written, remember, as a rational exponent. So if you have a rational exponent in a problem, it's really a Unit 2 one. We talked about them throughout the year, and as we go through examples, we'll talk about them throughout the year, but it's really a radical equation problem. It's Unit 2. With these, Sometimes we have excluded values, and that is going to affect our domain. And so we're really going to break this into two different groups, whether it is an odd root or an even root. If it is an odd root, so it looks like the cube root of x plus 2, you can cube root positives, you can cube root negatives, you can cube root decimals, so absolutely anything would work as an answer for this equation. Again, if I hypothetically wanted to just sit down and start plugging random things in. Obviously not the most effective way, but I could get a negative number and it's not going to make me bat an eye. I could get a decimal and I won't be surprised at any of those things. When it is an even root, you need under your root to be something more specific. We cannot plug anything we want into this because we're going to have some limitations. The limitation here is that you cannot even root a negative number. So what you are going to have to do is set your radicand, D-I-C-A-N-D, to be greater than or equal to 0 and solve. So I'm going to show you what that would look like on this problem. And then again, as we go through every unit in detail, I will highlight this specifically all the time. So if I wanted to know the domain for either of these two functions, what I would have to do is I would say, hey, x plus 2, whatever that is, has to be greater than or equal to 0, or I'm going to have an issue. I'm going to have a negative under that radical. When I solve this, that tells me that any x value has to be greater than or equal to negative 2. I'm going to graph this real quick. Greater than or equal to is a closed circle, and it's shaded to the right. What that means for me is my domain would be a bracket on the negative 2 all the way to infinity. So that would be the domain of either the square root or the fourth root problem there. But again, this is something we're going to hit a lot. The important thing is you're thinking about what is x allowed to be. Where that's positive and helpful in this problem, if I know the domain, if I know what x is allowed to be, and I solve this problem and I get negative 4, I immediately know that's an excluded value and I'm going to throw it out. If I get anything else, if I get 27 from my algebra, I at least know that is a possible answer. I'm going to have to check my algebra to make sure I didn't make a mistake, but it is at least possible as long as it falls in this domain. Unit 3 we did in two different groups. We did Unit 3A, which was specifically quadratics and anything of quadratic form. And we did 3B, which was just your higher order polynomials. Okay, and so this can look a lot of different ways. I'm going to give you some examples like before so that it jogs your memory a little bit. And again, like always, we're going to highlight these specifically as I go through each type. So from 3A, your quadratics, the most basic one could be like 3x squared plus 2x plus 1 equals 0, or whatever it equals. These are the problems that you factored or whatever it may be. We did also do ones that maybe it was 3x plus 2x to the 1/2 plus 1, where those were quadratic form because the first exponent was twice as big as your second one. So those we did teach in Unit 3. 3B is when you have higher degree. So now maybe we had 3x cubed plus 2x squared plus 1x plus 8, I don't know, equals 0. That was technically from 3B, just because it was higher order. Anytime, so these, the first one and the last one here, are technically just polynomial equations. Anytime you have a polynomial equation, we're going to think about it much just like we did in Unit 1. Into a polynomial equation, which means you just have a whole bunch of x's, either squared or cubed. All your exponents are positive whole numbers. You have integers there. You can plug in anything you want. I could plug in a 7 to this and I can actually evaluate it. I can plug in a 12 to this. I could plug in a negative number. I could plug in a decimal. You can evaluate that just fine. What that means for your domain is it's negative infinity to infinity. And again, if you think back to when we graphed polynomials, when we graphed in that chapter, that was always your domain. what I want you to notice, this second one has a rational exponent in it. Anytime it has that, this goes back to unit 2 because that means my problem has a square root. So for this problem, we would have to do what we did on the last slide, and I would set x has to be greater than or equal to 0, and that would be my domain. But again, we will hit this in detail once we get to unit 3. Once we get to unit 3 in the examples. Unit 4 was our rational equations, or our rational functions. And if you think back to unit 4, we had a lot of asymptotes, which means we do have excluded values here and things that x cannot be. Just to make up some examples, 3 over x plus 2 over x plus 1 equals 7. Or it could be more complicated with binomials and trinomials in the denominators, but that's really what these looked like. Thinking back to our equations, again, we did have excluded values, just like we did have asymptotes on the graph, and where that came from was your denominators, and the fact that we cannot divide by 0. Okay, and so we're going to have to take that into account. We are going to have to set each denominator equal to 0 and solve to find our excluded values, and that's again what x can't be. When we write our domain for this, we're going to write it much like we did in the graphing section where we did these to show those. So I'm going to show you what that would look like for this made-up problem here. For my excluded values here, we would get x cannot be 0 from setting x equal to 0 right here. From setting x plus 1 equal to 0, we could get that x can't be negative 1. Your domain for these, if you think back, was quite ugly, but I believe in you. When you think about this, if I'm thinking about a number line, if this helps you, I have negative 1 here, I have 0 here. X cannot be either of these, but x can be everything to the left, it can be everything in the middle, and it can be everything to the right. And so I'm going to really just write out exactly that. X can go from negative infinity to negative 1, but I can't get negative 1. But I can get anything between negative 1 and 0. And I can get everything from 0 to infinity. So I will warn you ahead of time, these domains will be your ugly ones. They will match what we did for our graphs. Again, that's what I want you to see, is that the graph domain matches the equation domain. Those are the x values you are allowed to get out. Not necessarily what you will get, but what you are allowed to get. But again, we will hit this in greater detail as we move forward through the reviews. Last but not least was our unit 5. With these, we had two types. We had our exponential functions and equations, and we had our logarithmic. Your exponential looked a couple different ways, but it basically boiled down to you had variables in the exponent, and it either equaled a number that you could rewrite as a common base, or like the one I just wrote that you couldn't. So maybe it looked one of those two different ways. Your logarithmic gave you a variable in your log, and so maybe it looked like one of these two. When we think back to that chapter, one of these you had things you couldn't get, and one of them you didn't. Your exponential, you can plug anything in the world into an exponent that you want. Again, if I really wanted to, I could sit here and solve this equation by just plugging in random numbers for x and waiting until I got a 7. And the numbers that I would be allowed to plug in would be absolutely anything. So what that tells me is my domain for exponential is always negative infinity to infinity. Again, that matches what we graphed before. For logarithmic, it's a different story because you cannot have a negative or a 0 inside your log. So what that means for us, we will set the inside of each log to be greater than, not equal to, 0 and solve. So for example, if I do that for this one, I would do x plus 1 has to be greater than 0. I would get x is greater than -1. Again, if you graph that, just to help you out, it's an open circle and all the numbers to the right. So my domain of my made-up problem here would be a parentheses -1 to infinity. And again, that's the same kind of domain that we had back when we graphed these. And that's really, again, what we're trying to tie together and help you to see a little bit better and be more confident with moving forward. Each of these things, again, I will hit in great detail going through each of the individual units. It is something we haven't specifically asked you to do with each of your equations before, even though we've done it with graphs. So I did want to take a minute and just highlight this by itself.